Decision Analysis 1, Lesson 5. Let's work with the problems in our Lesson 5 resources. We have 3 example problems there. The first is a payoff matrix decision analysis. And here we have 2 investment alternatives. One is a stock investment and the other is a CD. The stock investment varies according to the market conditions. So we're modeling 16% for a good market, 9% return for an average market, and negative 2% in a poor stock market. We are also modeling the probability associated with 3 states of nature. Market returns is a chance event, and we have 3 states. Good, we're modeling 0.1 or 10% of the time. An average market, 0.85 or 85% of the time. And the stock market will be what we consider a poor market at a probability of 0.05 or 5% of the time. Our second alternative is the CD investment. And for this problem, the CD has a very generous guaranteed rate of return of 8%. And the CD does not vary according to market conditions, so that's always 8% for all 3 states of nature. So now how could we use this information to make a decision? Well, we have a few different approaches. Using the Minimax approach, remember that's the optimistic approach, we would look for the best of the best returns, and that belongs to the stock alternative. So taking that approach, we would invest in the stock. We could also use the Maximin approach, where this is a more guarded position, looking for the worst outcome in each of the decision alternatives. Here our decision would be clearly to go with the CD. It has the best or the max of the worst returns for either alternative. These are good approaches, but they focus on only a best or kind of worst case scenario and make the decision accordingly. Another approach would be to use our regret matrix. So here we get something in between. According to the Minimax regret approach, we would want to minimize the regret by first considering on our regret matrix the maximum regret possible on our model for each of the alternatives. The stock, that's 10%, for the CD, 8%. Remember, regret is simply a missed opportunity, or what we call opportunity loss. So we're calculating our regret first and then using the Minimax regret approach. So taking the minimum of these 2 max regrets for either alternative, we would invest in the CD when using that approach. All of these methods are okay, but they don't employ the use of probability, and they don't consider all of the 6 outcomes possible here in making a determination. We focus on one thing specifically based on our point of view. But the expected value approach does consider all of the outcomes and weights each of those outcomes by the appropriate probability. So using our sum product calculation, we can obtain an expected monetary value, or simply an expected value. This is simply a weighted average, weighting each payoff by the corresponding probability. The expected return for the stock is 9.2%, while for the CD only 8%. So according to the EMV approach, we would invest in the stock. That would be our decision. We could do the same expected value calculation only using the regret matrix. This will always point to the same decision alternative. So we decided stock using the EMV. So we know we're going to decide stock using the min-EOL approach. The specific minimum expected opportunity loss is only 0.5%. And we get that also by using our weighted average, using the probabilities to assign weights to the regret totals. Now, another question we can consider here is the EVPI, or the expected value of perfect information. The EVPI is the maximum quantitative benefit, or we could say financial benefit, of always being in the right investment to maximize the return. Or in other words, if we were perfect. If we were perfect, we would get that 16%, the 10% of the time the stock market is good. We would get 9%, the 85% of the time that the stock market is average. Both of those are the max return possible in those market conditions. If we were perfect, though, we would be in the CD 5% of the time when the stock market is poor, and we would get that 8%. So the maximum that we could get if we're perfect, always in the right investment at the right time, according to our model, is 9.7%. But without being perfect, just using the average, we get an expected monetary value of 9.2%. The difference between them, 0.5%, is what we call the EVPI. So going from 9.2 to perfect, we can only improve the performance by 0.5%. If we were investing $30,000, the maximum financial benefit of information, or EVPI, would be $150. Our next example problem in Lesson 5 is a decision tree problem. Here we are trying to determine the best sequence for testing 3 components on printed circuit board. So this is a quality control application. If any one of the components on the circuit board fails, the board has to be scrapped. It does not meet quality standards. So we need to decide the most cost-effective way to do these tests. So there are 3 components, X, Y, and Z. And we can begin with any one of these. So we can begin here on our decision tree with test X. But we get to decide whether we begin with X or Y, or just scrolling down a little bit more, Z. Okay, so we're going to focus on that topmost branch. So let's just understand the logic of the decision tree. If we make the decision at node 1 to begin with test X, we could either pass or fail. If we pass, we can go on, but if we fail, the board must be scrapped. I have another worksheet here with some important given information to consider. We're only paying for the tests that we attempt. The probability of failure of component X is 0.125. So if we begin with X, we pay $1.75, but if we fail that test, the board is scrapped and we do not incur any additional cost. We only incur additional cost if we pass. If component X passes the test, then we can go on to either Y or Z. If we attempt all 3 of the component tests, the sum of the costs is $6.15. Let's look at that on the decision tree. So first of all, if we begin with X and fail, we see that the probability of failure of test X is 0.125. So 12.5% of the time we're going to fail that test and then only pay our total cost on the decision tree would be only $1.75. But some of the time we're also going to pass. So the probability of passing X is equal to 1 minus 0.125. So what we're looking for is one expected monetary value, the average cost of beginning with component X. So if this is the cheapest sequence, that's what we want to find out. So I have that table from the other sheet in a smaller version right here. And so let's fill in the rest of our decision tree. So if we start with X and pass, we can then decide to go to Y or to Z. If we pass Y, we can go on to Z. Likewise, if we pass Z, we can go on to Y. You can see that our outcome node, the triangle, makes it all the way across the decision tree. So in this case, we're going to pay for all three tests, which is $6.15. But if we start with X, we're going to pay for that. Remember, this is all assuming that we pass that first test X. So if we go on to Y and we attempt it but fail, we're only paying for X and Y. So equals $1.75 plus $2, or $3.75. If we begin with X and pass and decide to go to Z, once we attempt it, we pay for it. But if we fail, we're not going to incur any additional costs. So here our total cost for this sequence would be X plus Z. Now we need to input our probabilities. The probability of failure of component Y is given at 0.075. And the probability of passing would simply be the complementary event, or equals 1 minus the probability of failure. And once we input our probabilities, our weighted average, or our EMV, for this sequence is calculated. So we can see that EV is determined by probability times payoff, here a cost, plus probability times the cost. Let's do the probability for test Z. The probability of failure is given as 0.14, which means the probability of pass is equal to 1 minus 0.14. So now we get to make a decision. If we begin with X and pass, then the correct choice would be to go to Z, not Y, because going to Y is more expensive on average than going X to Z. So our decision tree here, we would want to carry over the minimum of those two expected values. If this were a profit problem, something where we want a bigger number, we would choose the maximum. And then we finally have one more expected value to calculate. Remember, we're only paying $1.75 12.5% of the time when we begin with X and fail. Now we know the 587 gets weighted at the probability of pass, which is 1 minus that, or 0.875. So that final expected value is determined to be 5.355. This is the average cost of beginning the testing with component X, and if we pass, going to Z. So the correct sequence for testing is X, Z, Y. The minimum average cost is 5.355. If you complete the rest of this decision tree, you could in fact confirm that the cheapest sequence is X, Z, Y with an average cost of 5.355. Our final example problem in Lesson 5 is another decision tree application. Here our focus is on deciding between two bid levels. So we're bidding for the rights to an oil and natural gas site. So we're trying to decide at node 1 between two bid levels. SGC could either bid high at 16 million or they could bid low at only 7 million. So quite a difference in cost between the two bid levels. So why would they bid high? Well, they have a competitor, NGC. NGC can either bid 10 million or their low bid, according to our model, is only 6 million. So if SGC bids high, they in fact are going to win the bid. According to the model, their competitor is only going to bid 10 million for a high and 6 million for a low. So if they wanted to be sure to win the bid, they would go with their high bid. But because it costs more, we want to be sure that that's necessary. So let's look at the decision tree and figure out our decision. So there is a very important additional chance event in this decision tree. One chance event is the competitor's bid. Is it high or low? But no matter what, high or low, the chance event of the site quality is important. So the reserve at this site could either be large, average, or unusable. We see those three branches or three states of nature for this chance event. If it's large, the expected net asset value is 120 million. If it's average, only 28 million. And of course, if it's unusable, the NAV would be 0. Now, the probabilities associated with large, average, and unusable. We're modeling a 0.15 probability of large, a 0.35 probability of an average sized reserve, which makes the probability of an unusable site 0.5. So rather high risk. That 0.5 is going to count heavily in our expected value, and the value being weighted by 0.5 is always going to be 0. Now let's fill in some costs associated with our high bid. These payoffs are going to change as soon as we do. So NGC has a 0.4 probability of bidding high, which makes the probability of their low bid the complement, or 0.6. When SGC bids high, they're going to have to pay that 16 million plus an additional 5 million if they win the bid. Well, SGC's high bid is greater than both 10 and 6. So when they bid high, they're going to have to pay that additional 5 million plus their $16 million bid, making the total cost, no matter what NGC bids, when SGC bids high, the cost is 21 million. So now our expected values are calculated. If SGC bids high, the expected value is 6.8 million, and that does not vary based on the NGC bid because it's no threat when SGC bids high. So the EMV for the high bid is 6.8 million. Let's scroll down and look at the low bid. Now we just need to update a little bit of information here for the low bid. If SGC bids low and NGC bids high, their cost will stay zero. SGC pays nothing because they would lose the bid, so they don't pay the 5 million and they don't pay the 7 million. But when SGC bids 7 and NGC bids low, which happens according to the model 60% of the time, or 0.6, they would win. 7 million plus an additional 5 million makes the total cost in this case 12 million. And the expected value of the low bid 15.8. But that only gets weighted 0.6 or 60% because the other 40% of the time the payoff for SGC is nothing. So the total expected monetary value of the low bid is 9.48. 9.48 is a better return than 6.8. So the correct decision for SGC would be to bid low. However, that decision is possibly sensitive to our assumptions. One critical assumption here is related to the probability of NGC's high bid. If their high bid probability increases, then that's a greater threat to SGC's low bid being successful. So our strategy table can show the correct bid strategy based on the probability of NGC's high bid. We know at 0.4 or 40% the correct decision would be to bid low. And if the probability of NGC's high bid were to decrease, the decision would stay bid low. It's less of a threat when that probability decreases. But let's see how much it can increase before the decision changes for SGC. So we can scroll up here. And here's our input cell. If we go up to 0.5, you can see that the low bid is still the correct decision. It has a higher EMV than the high bid. Let's go up another bit. At 0.6, the decision changes. At 0.6, the EMV for the low bid is less than the high bid. So on our strategy table, we would see that the decision strategy would change as soon as we get to about 0.6. So our decision is not very sensitive to that assumed probability, but at least somewhat sensitive as we see the decision change when our assumption is that wrong. When we go from 40% all the way up to about 60%, then our decision strategy would be affected.